3 independent research releases push models into realistic environments this week. Cat Coder V2.5 trains agentic code repair inside executable repositories. Induction Labs Photon 1 uses video-only pre-training to learn implicit desktop policies. FAIRChem V2 ships UMA, a single learned potential for molecules, catalysts, and materials. I'll explain what changed, how each system works, and practical trade-offs. KAT Coder V2.5 from the Kuaishou team is an agentic coding model trained to operate inside executable repository environments rather than just emit single-turn patches. The served model is available through Streamlake. An open-weight variant KAT Coder V2.5 dev is on Hugging Face under Apache 2.0. Tasks are triplets: a task description, an executable repo environment, and validation tests. Only patches that pass verification against those tests are retained as correct. Induction Labs released Photon 1, an imagination model, a sparse 106B-A5B mixture of experts transformer, pre-trained on 18 years of computer demonstration video. The filtered dataset is 575 million frames, sampled at 1 frame per second, about 552 billion tokens. Photon 1 was pre-trained for a single epoch. Frames are compressed by finite scalar quantization into 960 discrete tokens. A differential latent encoder makes the latents describe differences between frames. FAIRChem V2 publishes a tutorial using UMA, a universal machine learning interatomic potential. UMA exposes task-specific calculators for the OMAL, OC20, and OMAT domains inside the atomic simulation environment. The same pre-trained potential runs energy and force prediction, geometry optimization, vibrational analysis, adsorption energy cycles, crystal relaxation, and molecular dynamics. Access to some UMA weights requires Hugging Face authentication. Cat Coder's infrastructure uses AutoBuilder to synthesize repository build scripts and a verification agent to run them in isolated sandboxes. Acceptance parses structured test framework output. An environment is accepted only when more than 90% of expected tests are collected and outcomes reproduce across runs. The harness randomizes tool names, arguments, and prompt templates to reduce overfitting. Why these approaches matter. Cat Coder moves code models from single-turn generation to agents that act, test, and validate patches inside real builds. That helps address passing results that come from hard coding or test-brittle shortcuts. The paper reports retaining over 100,000 verifiable environments across 12 languages, and construction success improving from 16.5% to 57.2% after using pre-configured environments, templates, and a recipes library. Photon 1's central claim is predicting future latent states. From raw video teaches an implicit policy for desktop tasks without action labels. Induction Labs reports Photon 1 outperforms Gemini 3.1 flashlight on an internal benchmark, while using far less pre-training compute and serving at about 3 times lower cost. Those comparisons are internal and not independently reproducible. Induction Labs reports about 30,000 H200 GPU hours, roughly 4.4 times 10 to the 22 flops, and 40% MFU for pre-training. They report a break-even serving cost of 6 cents per 1 million input tokens and 60 cents per 1 million output tokens. Developer trade-offs differ by domain. Cat Coder needs curated executable repositories and sandboxed verification. It pays off for teams wanting high-confidence, test-anchored patches. Photon 1 suggests new possibilities for desktop automation from screen recordings, but requires a large, specialized pre-training corpus and VM rollouts for reinforcement learning fine-tuning. Induction Labs fine-tuned on fewer than 35,000 computer use trajectories before RL. FAIRChem's UMA reduces integration friction via ASE, but some weights are gated on Hugging Face and higher accuracy variants are noted. Each approach has clear limitations. Cat Coder's verification and anti-leakage checks add cost and complexity. Hint-based repair helps some zero-pass tasks, but they regenerate hint-free traces afterward. Photon 1's benchmark and cost comparisons are internal and depend on assumptions about competitors, so independent reproduction is needed. FAIRChem's UMA is practical, but higher accuracy variants and larger multi-GPU experiments are listed as extensions. All 3 write-ups were published July 26, 2026. Links to each primary article are in the description. Sources are the 3 MarkTech Post write-ups listed in the description: Kate Coder V2.5, Photon 1, and FAIRChem V2 UMA. Check the links for the full technical details, paper links, and model pages. Bottom line, these releases show 3 complementary routes for making models operate in realistic settings: verification-anchored code agents, video imagination for desktop policies, and a unified learned potential for chemistry and materials. Each removes a different friction point, but adoption hinges on data access, compute cost, gated weights, and reproducible evaluations. Watch for published benchmarks and evaluation code from early adopters.